For over a century, the global economy has run on a single, rigid blueprint. Manufacturers build massive factories in centralized locations, produce enormous volumes of identical parts, and ship them across the world. This is the traditional just-in-case inventory model. It requires huge amounts of capital tied up in vast warehouses, filled with physical stock waiting for a demand shock that may or may not happen. But as compounding global bottlenecks have proven, relying on complex, geographically dependent maritime networks leaves global logistics vulnerable to single-point failures. When we look at where heavy industry is heading, the answer isn't simply running mass production at a higher velocity. Speed alone cannot fix a system built on geographic dependency. Long-term viability now demands a complete reconceptualization of how goods are engineered and delivered. Industry must prioritize structural resilience over mere volume. The commercial aerospace sector has already developed a direct solution. Organizations like SpaceX have adopted an additive-first culture, using industrial-scale 3D printing to bypass the long lead times and high tooling costs of traditional supply chains. By printing highly complex components on demand directly from digital files, these companies replace massive warehousing with hyper-localized, decentralized production. They transition from just-in-case stock to hyper-efficient just-in-time manufacturing. This process also solves a major mechanical problem. Instead of taking dozens of individual plates and fasteners and laboriously welding them together, additive technologies allow us to consolidate sprawling assemblies into a single, continuous, monolithic piece. Eliminating those individual components immediately translates to fewer weak points where a weld might fail, and compresses the research and development cycle from months down to a matter of days. In this framework, additive manufacturing acts as a strategic asset for securing operational sovereignty. To actually realize these benefits, engineers have to discard their traditional methodologies. If you take a legacy CAD file designed for standard machining and send it straight to an industrial 3D printer, it will invariably fail. Success requires a highly specialized methodology called Design for Additive Manufacturing, or DFAM. This approach exploits the geometric freedom of a 3D printer, which is unbound by the physical limits of traditional drills or molds. A core principle of DFAM is minimizing material usage. Engineers deploy AI algorithms like topology optimization to calculate required mass. These simulate real-world stress, methodically stripping away any material that doesn't actively support a mechanical load. What you are left with is a highly organic, visually striking, bone-like structure. It provides the maximum possible stiffness while shedding every ounce of unnecessary weight. By adhering to these strict design constraints, engineers extract performance capabilities that are physically impossible to achieve with subtractive machinery. This localized additive blueprint presents a direct pathway for industrial growth on the African continent. Historically, Africa has navigated a severe structural deficit. Despite incredible mineral wealth, the continent relies heavily on an extractive economic model, exporting raw materials while its internal manufacturing sector contributes a disproportionately low 11% to its overall GDP. But disruptive technology provides a direct mechanism for strategic leapfrogging. African nations successfully bypassed capital-intensive copper phone lines to build world-class mobile cellular networks, and a similar jump is now viable in heavy industry. Nations can bypass the billions of dollars needed for polluting legacy refineries. Instead, they can transition directly into the era of smart, decentralized additive manufacturing, powered by local solar microgrids. With localized printers, communities can directly process native raw materials, like titanium ore or recycled biopolymers, into high-value end products, without relying on intercontinental shipping lanes. Direct digital fabrication changes the economics of resource sovereignty. It empowers nations to retain the value of their own materials, building their industrial future layer by layer, on their own terms. However, the most advanced hardware in the world, whether it's a metal powder bed fusion machine or a robotic concrete extruder, means nothing without a technically proficient workforce capable of running it. Achieving lasting industrial sovereignty requires a deliberate recalibration of educational frameworks. We need to foster innovators who inherently understand the complete end-to-end life cycle of digital design. We are starting to see this grassroots empowerment take shape. In Nairobi, Kenya, initiatives like the Lavington Girls' School Unity Art Club are bringing 3D printing technology directly into the hands of young students. This technology gives students a direct path from an abstract digital concept, solidifying layer by layer into a physical artifact. This creates a crucial pedagogical shift. It teaches youth that an impossible geometry is no longer a barrier to creation. It is simply an engineering constraint, waiting for an optimized mathematical solution. By bridging artistic expression with digital fabrication, these schools produce the designers and engineers who will direct the continent's industrial self-determination.